In this video, we're going to talk specifically about oxidation-reduction reactions. So this is on the topic of being able to classify reactions, and oxidation-reduction reactions are very, very common, and this comes up when we talk about batteries and electrolytic cells and just generally being able to produce electricity or use a battery to power other chemical reactions. So we're going to spend some time on this. But an oxidation-reduction reaction are basically reactions involving the transfer of electrons from one substance to another. Now, we've seen several oxidation-reduction reactions, which I might call them redox. That's the common way to just quickly say oxidation reduction. We'll say redox. But a lot of the reactions we've seen, and a lot of times the other classifications, they can also classify them as oxidation reduction reactions. So it's not like something is only single displacement or it's redox reaction, one or the other. It can be both of them. But anytime you have a metal and a nonmetal react, electrons are usually being transferred. So here we have neutral sodium metal, and then we also have neutral diatomic gaseous chlorine. But when these two react, what ends up happening is the metal, the sodium, like all metals, they'll want to lose electrons. And the nonmetal, the chlorine, will want to gain electrons. And this is exactly what happens. The sodium gives electrons over to the chlorine, and then we end up making sodium chloride, which, recall, sodium chloride is made up of sodium positive ion and chlorine negative ion. So the chlorine has gained an electron, and the sodium has lost an electron. So again, this is an example of a redox reaction. They're actually very, very common. The rusting of iron is also another very common everyday example. So iron will react with oxygen in the air to produce iron 3 oxide. So we've got iron 3 and then the oxide ions. Here's your neutral iron. So that's kind of like the chains before they rusted. This is oxygen gas from the air, making the iron 3 oxide, which is the rust that you actually see in the picture. But what's happening here is the iron is losing electrons. So we're going from the neutral iron to the iron that's charged, and here are the 3 electrons being lost. And then the oxygen gains electrons. So here's the diatomic neutral natural oxygen. And then here, this plus 4 electrons on the left side, that's showing a gain of electrons. And we produce 2 oxide ions where both of them are a 2- charge. So just remembering on key terms that we brought up in the last video, oxidized means you're losing electrons, and reduced means you're gaining electrons. So I suggest you make flashcards for those to help you remember those two terms. Now, oxidation number or oxidation state is what we are going to be spending some time calculating, because this is how you determine if a chemical reaction is indeed a redox reaction, is you will examine the oxidation number for the different elements in your chemical reaction. And if the oxidation numbers have changed, then you can classify the reaction as redox. But it's basically describing how many electrons have been lost or gained by an atom. So we've got a few rules. We're going to go through these rules here. Again, figuring out the oxidation number for each element on both sides of a chemical reaction. If there's a change in that number, it's redox. If there's no change in any of the elements, it's not redox. It could be something else like acid-base or something like that. So rule number 1, if you have a metal or a nonmetal in the free state means naturally occurring, so like iron solid or O2 gas or chlorine 2 gas, these are all examples of the element in their natural free state. It's going to have an oxidation number of 0. So all 3 of these examples have an oxidation number of 0. If you have an ion, and a monatomic ion, not a polyatomic, but if you have an ion, then its oxidation number is basically equal to its charge. So if you see sodium ion, its oxidation number is +1 because its charge is +1. If you see magnesium 2+ in a chemical reaction, its oxidation number is 2+ because its charge is 2+. If you see fluorine- in a chemical reaction, its oxidation number is 1- because its charge is 1-. Rule number 3, hydrogen atoms, or rather hydrogen ions, whenever you have hydrogens, they're going to have an oxidation number of +1. And we say usually because pretty much all of the time it's +1. There are some interesting exceptions when it's actually -1. And keep in mind, this is excluding the example where you have hydrogen diatomic gas, because this is like rule number 1 where it's in its free natural state. So here it's 0. But if you have hydrogen as in H2O, then the hydrogen in water is going to have an oxidation number of +1 because it's in a compound. So basically, anytime you see hydrogen in a compound, its oxidation number is going to be +1. Unless we're talking about in its free natural state, that's like rule number 1, then it's a 0. Rule number 4, oxygen is usually -2. So again, if we're talking about H2O, we just talked about how the hydrogen would be a +1. The oxygen would be -2, unless, of course, we're talking about oxygen in its natural state, then here it would have an oxidation state of 0. But if it's in a compound like we have here with the water, then it's going to be a -2. Now, there is one exception to rule number 4, which you should know about, but we will probably not see it, is if you have oxygen in a peroxide. So this H2O2, this is actually hydrogen peroxide, the same stuff you can purchase at the grocery store. The oxygen in hydrogen peroxide actually has an oxidation state of -1. So it's a common exception to rule number 4, but we may or may not see it. I just want you to be aware of it. Otherwise, oxygen is -2. For a molecular compound, rule number 5, the more electronegative element is assigned a negative oxidation number and is equal to its charge as an anion. So that's basically saying that if you have a molecular compound, the more electronegative element is more important, if you will. So let's say we have the compound, and for some reason my pen's not working well today, OF2. So let's pretend we have this compound, OF2. Fluorine is more electronegative, so it's more important. So the oxidation number for fluorine would be equal to its charge when it's an ion, which would be -1 for fluorine. And then the oxygen, well, that's another story when we talk about rule number 6. We'll explain what the oxygen is in this case. But the point is that we would start off, for using rule number 5, fluorine would have an oxidation state of -1 because when fluorine is an ion as fluoride, it has a charge of -1. That's what rule number 5 is trying to say. For rule number 6, for a compound, and this can be for ionic or neutral, but the sum of the oxidation numbers for each of the atoms has to sum up to 0. So if you have, for example, let's do the sodium chloride again. They're saying that the sum of the oxidation numbers for sodium and chloride have to add up to 0. So whatever sodium is, which it happens to be +1, and whatever chlorine is, which it happens to be -1, that has to add up to 0, and it does. 1 minus 1 is 0. We can use rule number 6, even though it says ionic, this still applies to covalent molecular compounds. We can use this to figure out what the oxidation state of oxygen is here. It still has to sum to 0. So if I use X to represent my oxidation state of oxygen in this compound, and then I've got a -1 for the fluorine, and there's 2 fluorines, it has to sum up to 0, which if you do this math, you'll have X minus 2 equals 0. X is going to equal to +2. So oxygen in this compound actually comes out to +2 because the fluorine is kind of more important, and it's going to keep its oxidation state of -1 based on rule number 5. But the point is that if you have a neutral compound, whether it's ionic or covalent, they have to sum to 0. The sum is equal to 0 if you have a neutral compound. If you're talking about a polyatomic ion, so now we're on rule number 7, for a polyatomic ion, the sum is equal to the charge of the ion. So let's say, for example, PO4 3-. This is the phosphate polyatomic ion. Recall that you should be trying to memorize your polyatomic ions. Now, the oxygen is the more electronegative element between phosphorus and oxygen, so it's going to be -2, and there's 4 of them. So I'm going to set this up like an algebraic expression, kind of like I did here. I'll use X to represent the oxidation state of the phosphorus, which I don't know yet. -2 for each oxygen, and there's 4 of them, so I'm doing -2 times 4. And then what rule number 7 is basically saying is since the charge of my phosphate is -3, I'm going to have equals -3 right there. And then if I wanted to figure out what the oxidation state for phosphorus is, I just solve for X. So I'll have X minus 8 equals -3. X is going to come out to +5. So the phosphorus actually has an oxidation state of +5 in the phosphate polyatomic ion. The point is what rule number 7 is saying is we did equals 3 here because the charge was -3 of the ion. So here's a couple more practice. So the oxidation number for aluminum, and it says aluminum metal, implying it's neutral. So it's going to be 0 according to rule number 1. Anytime you have a neutral element, metal or non-metal, in its natural free state, it's going to be 0 according to rule number 1. So this example here, what is the oxidation number for nitrogen in this ion? So because the charge of the ion is 3-, the oxidation number is going to be 3-. That's what rule number 2 said. Oxidation numbers for sodium and the oxygen in sodium oxide. So sodium, when it's an ion, it's a +1. So it's going to be +1. And then oxygen, this is actually a typo. This should say 2-, but here this is correct. But basically the sodium and the oxygen, those are what the charges would be, and that works out. So the rule number 6 was saying they have to sum to 0, and that checks out here because we'll have a +1 for sodium, and there's 2 of them, and then a -2 for oxygen, which is rule number 2. I think it was rule number 2. Oh no, it was rule number 4 talking about oxygen. But the point is it adds up to 0, which is what we needed because this is a neutral compound, so that works out. Okay, another example. So oxidation numbers for each element in ethyl alcohol. So we have carbon, hydrogen, and oxygen here. So one of the rules told us that hydrogen is always going to be +1. So this is +1 here. For oxygen, this should be a -2. But oxygen's -2, it's the most electronegative element in this trio. So we're going to go with whatever charge it would have. So then that just means that that's what we're left is to figure out what carbon would be. Now, they're doing something similar here, but I'm gonna do the same thing but write it differently. But we're going to set it up as an algebraic expression to figure out what the oxidation state of the carbon is. So since there's 2 carbons, I'm going to write a 2, and I'm going to use X to represent the unknown oxidation number for carbon. Then I'm going to do plus, and there's 6 hydrogens, and each one is a +1, and then there's 1 of the oxygen, which is -2. And this all has to add up to 0 because this is a neutral compound. So I basically have 2x plus 6 minus 2 equals 0. 2x plus 4 equals 0. 2x equals -4. 2 is going to, and then x is going to equal -2, and that's the result that they got here. They just wrote it a little bit differently. So this is a strategy that you can use to figure out the oxidation state for any element in a compound. And the starting point is we started off following our rules. Hydrogen was +1, oxygen was -2, and then we set up our algebraic expression to figure out the rest of it. So here's another example. So hexachlorobenzene. So we've got C6Cl6. So for chlorine, because chlorine is the more electronegative element, we're going to assume that it's got the same oxidation number that it would have if it was an ion, which was -1. So then figuring out for carbon, same thing, we can set up an algebraic expression. So I've got 6 carbons, and I'll use X to represent the unknown oxidation number, which we're trying to figure out. And then I've got 6 chlorines where each one is -1. And since this is a neutral compound, I'm going to say equals 0. So I've got 6x minus 6 equals 0. 6x equals 6. That means x is going to have to equal +1. And that's the same conclusion they got here. They just wrote it a little bit differently. Okay, here's another one where it's a polyatomic ion. So here, notice the ion, it's got a charge of -1, so we're going to have equals -1 when we work this one out. So first off, between chlorine and oxygen, oxygen is more electronegative, so we're going to go with that one. You can use your you can use ptable.com to verify that, or use the chart in the book, but oxygen should be more electronegative. And then for chlorine, we'll use an X to represent for chlorine. So then I'll say there's 4 oxygens where each one is -2, and then it equals -1. So X minus 8 equals -1. X is going to equal +7. So even though chlorine normally has a charge of -1 when it's an ion, because we're forcing it to bond with an oxygen, which is more electronegative, it actually has an oxidation number of +7, which should feel kind of weird, but that's how it is. So they got the same result, they just wrote it a little bit differently, but they're following the same thinking, same strategy here. So when you do have exchange of electrons, again, we call it a redox reaction. An oxidation-reduction reaction is also called a redox reaction. Anytime we have a transfer of electrons, we call it redox. So here's an example where we have a different one from before, so iron, but this time it's reacting with sulfur. And we make iron sulfide, and it's iron 2 sulfide because sulfur is usually -2. And if there's one iron with this one sulfur, then that means this must be a +2. So the sulfur, this is the key thing, the oxidation state for sulfur changed from 0 to -2 because this is iron in its natural state, so it has an oxidation state of 0. This is sulfur in its natural state. It's just sulfur solid. Its oxidation state was 0. And then here we had -2 and +2 for the elements on the product side. So sulfur changed from 0 to -2, and iron changed from 0 to +2. So because the oxidation numbers changed for our elements, we can classify this reaction as redox. It's also a synthesis reaction because we have A plus B makes some new compound AB. So it's possible to have a reaction being classified as more than one thing. So it's not just a synthesis, it's also a redox reaction. So since the iron in our example lost electrons, we're going to say it's oxidized. And this is what we call the half reaction for iron. So it's just kind of the iron half of the reaction that we see down here, where the +2 electrons on the right side is how we represent losing electrons. And then the sulfur, it gained electrons. We call that reduction, or it's being reduced. And writing +2 electrons on the left side is how we represent electrons being gained. We never ever write like -2 electrons to represent a loss. We don't write it like that. And then here, this is kind of, we call these tie lines, these red and blue lines that are here, but the oxidation state for iron went from 0 to +2, sulfur went from 0 to -2. This is another way to just kind of visually represent and keep track of what's going on in the redox reaction. You have 2 electrons being lost by the iron, and the sulfur gains those 2 electrons. So oxidation is loss, reduction is gain. Very important to remember that. 2 brand new key words. So oxidizing agent is the substance that causes the oxidation in the other substance. So what's being oxidized? The iron is being oxidized. What caused that oxidation? The sulfur. So the sulfur caused the oxidation, so the sulfur is the oxidizing agent in our example here. Reducing agent is the substance that causes the reduction. So what was being reduced? It was the sulfur. Sulfur was reduced. Can't spell. So what caused that reduction? The iron caused it. So the iron is the reducing agent in this example. I don't like to use these two terms quite so much because they obviously can be confusing. Iron is being oxidized, yet sulfur is the oxidizing agent. But you might see these terms and we might use these terms occasionally, so that's why you should be familiar with them. So in a redox reaction, this is an important concept, is you always have something being oxidized and something being reduced. You can never ever have just one thing being oxidized and nothing else in the reaction being reduced. If something is losing electrons, something else must be gaining them. And then the total number of the electrons lost must equal the total number gained. And this will get into balancing redox reactions, which we're not going to talk about yet. We'll talk about it later in the course, however. But if something is losing electrons, something else must be gaining. If something is being oxidized, then something else must be reduced. So they always occur together. You cannot have something losing electrons and being oxidized if nothing is gaining those electrons and being reduced. This graph is kind of nice, looking at the oxidation numbers. So for example, if your oxidation number is changing from -3 to +4, that's going to be oxidation. So recall that electrons are negative. So to go from a -3 up to a +4, you'd have to lose 7 electrons to do that change. And if you went from like a +7 down to a +5, for example, because electrons are negative, to go from something that's not as positive to something that's less positive, you'd have to gain electrons to do that. So you can refer to this chart if you are trying to figure out some oxidation numbers, and if something's being oxidized or reduced, this is a nice chart that you can refer to. Now, normally when we write redox reactions, we'll use these tie line methods to kind of spell it out, keep track of what's going on. So in this example, we're just going to, practice with these new terms. So we're going to identify the reducing and oxidizing agents and whatever's being oxidized and reduced, and also take a look at the electrons. So we've got copper sulfide plus hydrogen gas making copper metal and hydrogen sulfide. So going through each element, and this is what I suggest you do, is every single element in the chemical reaction, write down what the oxidation number is. So here we have hydrogen in its natural state. So that's 0, and here's copper in its natural state, so it's also 0. Here's an ionic compound, so the sulfur would be a -2 because that's what sulfur would be if it was an ion. It would be -2, which means this copper must be +2 because this is a neutral ionic compound. So the sum of the oxidation states must equal 0, so +2 and -2. And then something similar over here. However, we have hydrogen, which one of the rules said hydrogen is pretty much always going to be +1 in the compound. And this sulfur is going to be a -2. And this still satisfies the sums to 0 rule because we've got 2 hydrogens at +1 each with a -2, and that's going to sum up to 0 quite nicely. So now we've got all of our oxidation states mapped out for each element in the entire equation. So then looking at what has changed, so notice that sulfur did not change. Sulfur was -2 and it stayed at -2. So sulfur, no change. You will often see this. Some of the elements will have no change in the reactions, and that's okay. What did change, however? The copper. Copper went from +2 to 0. So +2 to 0, that means it must have gained electrons to do that because, again, electrons are negative. The hydrogen went from 0 to +1, so it had to lose electrons to make that change. So that means the hydrogen was being oxidized and the copper was being reduced. So we'd say that the hydrogen gas is the reducing agent and this substance was the oxidizing agent. Now there's one difference between oxidation and oxidizing agent. Usually when we have the word agent in front of it, it's what is the substance responsible for the oxidation and reduction, as opposed to what is the element that's responsible for it. So if you were to go into the stockroom of the chemistry laboratory, you don't pull copper ion off the shelf, you pull copper sulfide off the shelf. So that's why the copper sulfide is being called the oxidizing agent, not the copper. And then for the hydrogen, we're not saying hydrogen is reducing agent, we're saying that the hydrogen gas, the diatomic hydrogen gas, is the reducing agent. Now, normally with these redox reactions, we'll write them out as ionic equations. And again, this is something we're going to get into later, but then we can work on balancing. But quite often, you will have reactions written like this one is. So we've got, ions written out here. So this is what we mean by an ionic equation, is you have ions written in the equation as opposed to everything as just a neutral compound. So we're usually writing it this way. Redox reactions in aqueous are most often shown like this in the ionic form, because this readily shows us the change in oxidation number for many of the compounds. So like iron, we can easily see that it has an oxidation state of 2+ and it changes to 3+. So that's something important that's clearly happened. The hydrogen here is +1, but then here's hydrogen in a compound, so it's also going to be +1. So hydrogen is no change. Manganese, so here's manganese over here, not sure what it is upon inspection, but here it's a 2+. We could do our algebra trick to figure out what it is, and they tell us the answer is +7, but let's work out really quick how they got this +7. So I'm going to use X to represent the oxidation state of the manganese. And then there's 4 oxygens where each one is 2- according to our rules. And then it sums to 1- because it's a polyatomic ion. So this is our expression that we're going to solve for X. X minus 8 equals -1. X equals +7. So that's how they got the +7. So here it's +7. And we notice that manganese changed from +7 to +2. So that's another important change. So because the iron changed from 2 to +3, from +2 to +3, it had to lose an electron, so we say oxidized. Manganese went from +7 to +2. It had to gain 5 electrons to do that, so that's why we say it's being reduced. So often you'll see redox reactions written in this ionic form because it's much easier to spot the changes, the change in oxidation numbers and how the electrons are being transferred. So this is the same example that we just saw, but we're using the tie lines this time. So going from iron 2 to iron 3, and also notice this is kind of like a cleaned up version of what we saw on the previous slide. But because here we don't have the H pluses that were here, and the waters that were on this side, those have not been included yet anyway. And that's okay because the hydrogen and the oxygens, those weren't what was changing, so we kind of left them out. But to map the reaction to show how everything happens, we have our little tie lines. So again, iron went from 2+ to 3+. That means it must have lost 1 electron, so we call it oxidation. And then the manganese went from +7 to +2, so it had to gain 5 electrons to do that. We call that reduction when it gains electrons. Now, you may remember, hopefully you do remember from a few slides earlier, the electrons have to be balanced. For however many electrons are lost, the same number needs to be gained. So in order to remedy that in this example, what we would do is balance the redox reaction, but that is a whole nother topic because it's not just a matter of balancing the atoms like we've done with other practice problems. It's a little bit more involved, but we will have another lecture video specifically for that topic. And then in terms of the agent labels, so because the manganese was being reduced, we call the permanganate ion the oxidizing agent. And then because the iron was being oxidized, we call the iron the reducing agent. So again, flashcards to try and remember all of these terms.